This video is all about solving equations in which there are vectors in the equations. There's a few things we need to be careful about in addition to all of the regular things that you need to remember about basic algebra and solving equations in general. So we're going to talk about solving equations that have vectors in them and how to take a vector equation and turn it into an equation that only has scalars. That's going to be a trick we're going to use to solve problems. So just to remind you about a few vector math tips and rules, remember that you are never allowed to divide by a vector. I've said this many, many times, and we've never really had a case where we wanted to divide by a vector. And today we're going to see some examples of when you might feel the urge to divide by a vector. I'm going to give you some ideas of what to do instead, because it just doesn't exist. There's no such thing as vector division. You are allowed to always, you can add, subtract, you can multiply vectors by scalars. These are all operations that we've practiced, we've done in many different ways, so you're always allowed to do that. Remember that when you perform a dot product, the result of a dot product is a scalar. When you perform a cross product, the result is a vector. So be very careful when you're thinking about how to solve an equation. You might want to do one or the other, but typically, if you want to turn a vector equation into a scalar equation, we're going to use the dot product a lot to take a vector equation and turn it into a scalar equation. And then the last thing I want to mention is that when possible, it helps to write your vectors in component form and plug those expressions into an equation that you might have. It'll help you along the way to solve for various variables within that equation if everything's expressed in terms of the unit vectors x hat, y hat, and z hat. So let's get started with an example. Let's say that you have this equation here that VF equals VI plus AT, where VF, VI, and A are all vectors. Let's say that you want to solve for vector A. This expression, I want you to approach this just like any other algebraic expression. I want to get A all by itself. And so following our rules of algebra, I am going to subtract vector VI from both sides. That's allowed. So now I have VF minus VI is equal to A times T. And if I want to get A all by itself, now I'm going to divide by T. T is a scalar. It does not have a little arrow symbol on top of it. So I'm allowed to divide by T. That's fine. And so my final expression is just vector A is VF minus VI divided by T. So very similar to just basic algebra. I did not ever feel the urge to divide by a vector so I can follow my general rules. So remember, you're always allowed, you can add, subtract, you can multiply vectors by scalars. None of that breaks the rules of vector math. Just be careful that you do follow the rules of algebra. You must always, whatever you do on one side of an equation, you have to do on the other side. So remember the rules of basic algebra. All right, let's do another example. Let's say you get this equation, F equals MA, where F is a vector and A is a vector, and we want to solve for M. I am feeling an urge right now. I want to divide by vector A. So whenever you feel that urge, you need to follow this advice instead. Whenever you feel the urge to divide by a vector, I want you to take the dot product instead. When I say take the dot product, whatever vector you felt the urge to divide by, now you should take the dot product with that vector instead. And again, whatever you do on one side of an equation, you must do on the other side. So I'm going to take the dot product with vector A on both sides of this equation. And so notice how that's going to simplify things. When I do a dot product, I'm going to get scalars in the end. Recall the definition of the dot product. It's the norm of the first vector times the norm of the second vector times the cosine of the angle between them. So I'm going to use that definition and simplify this expression. I'm going to call theta is the angle between vector F and vector A. And all of that is going to be equal to M. And now I'm going to do the dot product between vector A and vector A. So it's the norm of vector A times the norm of vector A times the cosine of the angle. If a vector is dotted with itself, a vector is by definition parallel to itself. And so the angle between any vector with itself is 0. So the angle over here is 0. is the angle between A and A. All right. And now notice I have no more vectors in this equation. All of my answers, all of the things in this equation are now scalars. Remember, a norm is a scalar. And so I'm going to continue my algebra and solve for M. All right, so I'm going to divide both sides of this equation by the norm of A times the norm of A times the cosine of 0. So that cancels all that stuff out on the right-hand side of my equation. And now I'm just going to simplify stuff. I see that the norm of A is in the numerator and in the denominator. So one of these is going to cancel with one of those. The cosine of 0 is just the number 1. And so in the end, my expression for M is just the norm of F times the cosine of theta, all divided by the norm of A. And again, theta is the angle between vectors F and vector A when they are drawn tail to tail. All right, so I have my final expression. I solved this equation and I did not divide by a vector. All right, here's another example. So let's say I have this equation here. I need to solve for the norm of F and for the norm of T. I have one equation, but two unknowns. The rules of algebra say that I need as many unknowns that I have, I need that many equations to solve for it. So I'm a little bit stuck right now. How am I going to solve? I have two unknowns, but only one equation. The trick here is whenever you have an equation that's in component form, let's use the dot product to eliminate some variables. So if you think about it, I see x hat and y hat on both sides of this equation. Recall for the Cartesian coordinate system that x hat dotted with y hat would give me a 0. So let's be strategic and let's take the dot product of this equation with x hat. And then separately, let's also take the dot product of this equation with y hat. And what that's going to do is going to take one vector equation, and it's actually going to create two scalar equations. So I've already written it out here. I can see on this side, on the left-hand side over here, I took the dot product with x hat. And on the right-hand side, I took the dot product with y hat. And so I'm going to work on the left-hand side with the dot product with x hat, and let's simplify this and see how it becomes an equation with only one unknown. And so if I distribute the dot product, I get negative 0.3 times the norm of t, x hat dot x hat, plus 0.5 norm of f, x hat dot y hat. Now I'm going to distribute the dot product on the other side of the equation. And so because of the how the unit vectors in the Cartesian coordinate system are perpendicular to each other, x hat dotted with y hat is 0. X hat dotted with y hat is 0. X hat dotted with x hat is the number 1. And so these terms that have the x hat dot y hat go away. And so I've eliminated one of my unknowns. And so now I can continue on with this equation and I only have one unknown variable. So negative 0.3 times the norm of t is equal to 0.54. And so the norm of t is just going to be negative 1.8. All right, and now I can do all the same stuff on the right-hand side of this equation. I'm going to distribute the dot product. And again, these terms that have x dot y are going to die. They're going to go to 0 because that dot product is 0 because those two unit vectors are perpendicular to each other. Y dot y is the number 1 because it's a unit vector dotted with itself. It's very important that that was a unit vector. So this equation becomes 0.5 times the norm of f is equal to 0.23. And I get that the norm of f is equal to 0.46. And I have a final answer. So that was how I took one vector equation and I created two scalar equations. That's a very important technique to use to solve for unknowns. The last thing I want to do in this video is kind of start introducing you to solving physics problems. It's very rare that I'm just going to give you an equation and be like, solve this for F. Like, I'm going to give you a word problem. There's a scenario because the physics is showing you the relationships between various physical quantities. And so I'm going to start giving you word problems to start putting and using these generic or these general problem solving steps, because this is what you're going to see in physics class more often than not. What you want to do is try to use these general steps of how to solve a word problem. The first step is to sketch and translate. Draw pictures. And if you've already been given a picture, put annotations or different marks on the picture to help you understand what's going on in the picture. Translate means to write down a list of unknown quantities and known quantities. So take the symbols and the numbers out of the problem and write those down so that you can see them and use them as you're thinking about how to solve the problem. The next step is to simplify and diagram. What you should do in this step is choose a coordinate system. Choose an X hat, a Y hat, and a Z hat. And it's up to you how those things should point. You get to decide how they point. And you might not want them to point like perfectly vertical and horizontal. You might choose to have them tilted depending on the problem. The next step is to represent mathematically. That means to look for equations that relate various physical quantities with each other. So the equations that you've seen so far in this presentation, like F equals ma, that's a relationship between force and mass and acceleration. You're going to need some equations to solve for your unknown quantities. And within that step, you should rearrange those equations to solve algebraically for the quantity you're looking for. The last step is to actually solve and evaluate. Now you get to plug in any known variables or quantities and actually solve and get a final answer for that unknown that you have been looking for. Evaluate means to check the units on your final answer. Do they make sense with all the other units that are in the problem? And does your final answer make physical sense? Is it completely unreasonable, or could it be within the realm of the parameters of your problem that this could be a final answer? So it'll take a lot of practice to do all these steps and become good at this, but you should start doing these things. And I'm going to give you some more opportunities to do so. So we're going to finish this video by doing a word problem. And a lot of it is, I'm going to give you a lot of the information. You're just going to be responsible for the vector math. So you don't really know a lot of the physics yet. I'm going to feed you the physics and you guys are going to do the vector math. So in this problem, we have a ball that's falling out of the basket of a hot air balloon, and it's going to travel to the ground as it falls. The ball had an initial velocity, so this is a vector, VI, is 12 meters per second in the X hat direction. At a time of t equals 3 seconds, so t equals 3 seconds, the ball has a displacement vector of this value right here, 41 meters X hat minus 88.4 meters Y hat. And we want to find the scalar component in the X direction and in the Y direction of the acceleration vector A of the ball while it's falling. So if you can kind of picture this, I've already chosen a coordinate system for you. Looking at our initial velocity vector, that means that this ball was initially traveling horizontally with 12 meters per second in the X hat direction. So that's our velocity vector was horizontal based on our coordinate system where X's to the right are positive. And now at 3 seconds later, it's going to have a displacement. That means its position will change by this much. 41 meters X hat plus negative 88.4 meters Y hat. So that's a vector that points to the right and downwards. Because in our system, X hat to the right is positive and Y hat up is positive. So for our our displacement vector, 41 meters X hat, that's positive, that's 41 meters to the right. Negative 88.4 meters Y hat, that's down 88.4 meters. So that's why I've drawn my displacement vector kind of going downwards. And then I've given you the mathematical relationship between all of these quantities. Our goal is to find the acceleration vector and to extract the scalar components of that vector. So you can express any vector as the sum of its components. So we can maybe call this acceleration the ax times x hat plus ay times y hat, where this a sub x is the scalar component in the x direction. And this one would be the scalar component in the y direction. All right, and that's our goal, is to find those two things. So we've kind of sketched and translated this problem, or actually I've sketched it and I've kind of simplified it. We chose a coordinate system. On this next slide over here, I have translated the problem. I wrote down my known variables and my unknown variables, and I wrote down some equations that might help us solve this problem. So what we want to do now, we're kind of in that step where we are representing things mathematically, and I want to solve that equation for the variable we're looking for. So I'm going to take this known equation and solve it for A. So I'm going to use just basic algebra. So the first thing I'm going to do is I am going to subtract the VI times time from both sides. Okay, so I'm still trying to get A all by itself. Now I am going to multiply both sides by 2 divided by t squared. All right, and so that's going to get rid of my 1/2 and my t squared, and now I'll finally have A all by itself. So I'm going to write down A is equal to 2 over t squared delta r vector minus VI vector times time. All right, so this is my mathematical representation of what the A vector is. Once I get that A vector, then I can get the scalar components out of it. So let's keep on going. Now we're going to plug in, we're going to solve and evaluate. So we're going to start plugging in our known variables. So I'm going to kind of come up here. My vector A is 2 over t squared. T was 3 seconds. All right, delta R is 41 meters x hat minus 88.4 meters y hat. And then from that, I'm going to subtract VI times time. So VI was 12 meters per second x hat, and that's going to get, again, multiplied by the 3 seconds. All right, now I'm going to kind of just use some arithmetic and simplify this stuff. So vector A is 2 divided by 9 seconds squared. And I have 41 meters x hat minus 88.4 meters y hat minus 36 meters x hat. Notice that the 12 meters per second times 3 seconds, those seconds cancel out, and that's how I got my 36 meters. Okay, I'm going to continue with my algebra. I'm going to combine terms that have the x hats together. So A is still 2 over 9 seconds squared, 41 meters x hat minus 36 meters x hat. That's going to be 5 meters in the x hat direction minus 88.4 meters y hat. Okay, I can't combine those anymore. Now I'm just going to distribute the 2 divided by 9 seconds squared within those parentheses. So I'm going to actually do that math. So 2 divided by 9 times 5 is 1.11 meters per second squared x hat minus, okay, now I'm going to distribute the 2 divided by 9 times 88.4. So I get minus 19.64 meters per second squared y hat. So that's my acceleration vector. If I just want the actual scalar components, remember that the scalar component is given by the dot product of the vector with the unit vector that describes that direction. And so if I want to get the scalar x component, a sub x, I'm going to do this vector A dotted with x hat. And I think I can convince you without actually writing this down. If I take that vector expression for A and I dot it with x hat, the only term that is going to survive is that 1.11 meters per second squared. It'll have x hat dot x hat. That's just the number 1. So the scalar component in the x direction is 1.11 meters per second squared. the scalar component in the y direction. Likewise, go back to your expression for a, the vector for a, and dot it with y hat. X dot y is 0, y dot y is 1, and so the y component is going to be the negative 19.64 meters per second squared. All right, and that is our final answer. For this particular problem, we have the scalar components of the acceleration of that ball as it falls to the ground.